Hello, this is part 4 on my single variable calculus 2. In this video, we're going to talk about moment, which is another application of integrals. First, we're going to talk about what moment is, and then we are going to talk about how to use integrals to evaluate moment and center of gravity. So imagine you have a seesaw and you want the seesaw to be balanced. So you have two objects sitting at both ends of the seesaw. So when do we have a balance in a seesaw? When the distance multiplied by the mass is the same on the two sides. So this quantity d times m must be the same to have a balance. Now, this quantity is called moment. So moment is tendency of rotation. So in other words, moment depends on two things. It depends on mass and it depends on distance. So these two things give us the moment. So that's how we define the moment, the distance and mass. Now, in order to find the distance, we need either a center of rotation or an axis of rotation. In this video, we're going to talk about moment relative to two axes, relative to the x-axis and y-axis. So how do we define the moment? Given a point on the plane with mass m and location xy, so we have a mass m that is located at the point xy, we can define the moment relative to the x-axis and the moment relative to the y-axis. So the moment relative to the x-axis would be mass, which is m, times the distance to the x-axis, which is y. So the moment relative to the x-axis is, we usually denote that by m sub x, it's the mass times y. And moment relative to the y-axis would be mass times the distance to the y-axis, which is x. So moment with respect to the y-axis would be m times s. So it is the same thing, except that it's respect to the x-axis. Now, a single point with a given mass is called a point mass. So a point mass is mass concentrated at one point, at a single point. If I have a bunch of point masses, then I can think about what is the moment of the entire object, the several different points together relative to an axis. And the total moment is just the sum of the moments of those point masses. So let's do an example. Three masses, 1, 2, 4, are positioned at these 3 points, and we want to find their moment relative to the two axes. So let me first draw a diagram. So we have point 1, 3. So 1, 3. So the first mass is right here. We have the point -1, 2. So the next mass is right here, and the next one is -3. So -2, -3, and -2. So the next mass is right here. So we want to find out the total moment of these three relative to the x-axis. So the moment relative to the x-axis would be mass, which is 1, times the distance. The distance is the y-coordinate, 3, plus 2 times distance to the x-axis again, so that's also 2, plus 4 times distance to the x-axis, that's the y-coordinate, which is -2. So note that moment can be negative as well as positive. So that's 3 plus 4 minus 8, which is -1. Moment relative to the y-axis, again, we're multiplying each of the masses, 1, 2, 4, with each of the y coordinates. So 3, 2, and -2. That's how we get the total moment. Moment with respect to the y-axis would be 1 times the x coordinate, so 1, plus 2 times -1, plus 4 times -3. And that is -13. So that's the total moment relative to the x-axis and relative to the y-axis. Okay, so now we can use moment to define what is called the center of gravity or center of mass or centroid. So what is the center of gravity? So center of gravity or centroid of a collection of point masses is the point in which placing the total mass at that point would create the same moment relative to both axes. So in other words, let's say you have these 3 points and the masses are 1, 5, 8. Now I'm going to take away all of these 3 masses and replace them with 1 point mass with the total masses of these 3, which means 1 plus 5 plus 8. So we're going to place 14 here in a way that mx is the same for the single point 14 and the 3 points together, and my is the same for the 3 points and the single point that is located at the centroid. So let's imagine the center of mass is located at x bar and y bar. So this is the center of gravity. If that's the case, the moment relative to this would be the total mass. Let's say we have, this is of point masses m1 all the way to mn located at x1, y1 all the way to xn, yn. We're going to find the moment for both of them, and then we set them equal. So what is the moment relative to the x-axis? Moment relative to the x-axis would be the total mass times y bar. And on the other hand, it is m1, y1 for the n masses all the way to mn, yn. And I can do the same thing for m sub x as well. And what I would get is these formulas, these 2 formulas here. So m sub y is going to be m1 all the way to mn times x bar, which is the same as m1 x1 all the way to mn xn. So that means x bar is equal to m sub y over the total mass, which would be m1 x1 all the way to mn xn, divided by the total mass m1 through mn. And y bar would be m sub x divided by total mass, which is m1 y1 all the way to mn yn, divided by m1 plus all the way to m. So that's the formula for the center of mass. Let's find out what the center of gravity is for the example that we just did. So find the center of gravity of the 3 point masses in the previous example. Just to recall, we had mx, we found mx. We go back and look at what mx was. Mx as -1 and my as -13. So we know that x bar would be my over mass. Now, what is the total mass? Mass is 1 plus 2 plus 4, which is 7. They gave us those numbers in the problem. So they told us that the masses are 1, 2, and 4. So that gives us 7 as the total mass. So this would be -13 over 7. And y bar would be mx divided by mass, which would be -1 over 7. So the center of gravity is going to be -13 over 7, comma, -1 over 7. So far, none of these have used any calculus. These are all basic stuff from physics. So now we're going to talk about how to relate this with integrals. Now, notice that both of these examples that we did were for a bunch of point masses. Now imagine you have the region bounded by the graph of two functions. So let me draw a diagram for this. I have a function f of x. I have a function g of x. This is y equals f of x, y equals g of x. And I want to find the center of mass of an object positioned at this R. So what is the center of mass of that? Let's assume that density is 1. In other words, the density is the same across this object. If that is the case, then we can basically say that mass is the same as area. So instead of using mass, we're going to use area. So given that, we can find the moment relative to area. So let's figure out how to find the moment with respect to the y-axis and moment relative to the y-axis, x-axis. Let's take a sliver of this region. So take a thin sliver of R. Let's find out what's the moment. Well, moment relative to the y-axis is going to be, well, we have to find mass, but in this case, we're using area. So it would be area times distance. What is the distance of that to the y-axis? Well, that's just x. Now, what's the area? Well, the area is base times height. Area of this is base times height. Base of this is delta x, and height is this length right here, which is f of x minus g of x. So this would be our height. So this would be f of x minus g of x delta x. So that's area times x. Now, once I take a bunch of these slivers and I add them up, I would get a Riemann sum. So let's take the interval from a to b. Let me mark that here. So this is a, and this is b, and I divide this interval. So divide a b into sub-intervals. So x0 is a, x1 all the way to xn is b. And then what you do is you pick, similar to what we have done before, pick zi inside xi minus 1 xi. And then we can approximate the moment with respect to the y-axis by the sum of these formulas. So f of zi minus g of zi delta xi times zi. I equals 1 to n. As we let delta xi go to 0, we get the integral of f of x minus g of x d times x, because there's a z at the end. So we do times x dx from a to b, and this would be m sub y. So I have the formula for m sub y as integral of f of x minus g of x times x dx. So that's the moment relative to the y-axis. Now let's also do the moment relative to the x-axis. For moment relative to the x-axis, let me draw the diagram again. I have two functions here, and again bounded between a and b. Top one is f of x, bottom one is g of x, and I have a sliver here. I'm going to find the moment of this sliver relative to the x-axis, and then we'll turn that into an integral. So again, we'll have to find the area, and then we'll have to find the distance. So moment relative to the x-axis would be area times distance. Area is the same thing. Area is f of x minus g of x delta x distance. Well, distance is a little bit different. This one here is g of x, and this one here is f of x. So the largest distance is f, and the smallest distance is g. The center of mass of this is like in the middle. So it makes sense to say that the average distance is f of x plus g of x over 2. After you multiply this, you have difference of squares here. You get f of x squared minus g of x squared over 2 times delta x. And that turns it into this formula that the center of, that the moment relative to the x-axis is 1/2 integral from a to b of f of x squared minus g of x squared dx. So those are the formulas. And then we have this formula is the exact same thing that we had before. X bar is m sub y divided by, we had mass, but we replaced mass with area. So x bar is m sub y divided by area. Y bar is m sub x divided by area. So now we're going to go over a few examples. Find the center of gravity of the region underneath the curve y equals cube root of x and above the x-axis. Okay, so let's go ahead and do this problem. So we have cube root of x, which looks like this, but they said x is between 0 and 1. So we have this region. So this is our region underneath this, above the x-axis. Yeah, so this is our region R. I have to find center of mass. So we need to find m sub x and m sub y, and then also area, and then use the formula. So m sub x, so again, going back to the formula, m sub x is 1/2 integral from 0 to 1 f of x squared minus g of x squared dx. And m sub y is integral from 0 to 1 x times f of x, which is cube root of x, minus g of x, which is 0. And then we'll have to integrate these. So these are easy integrals. These are just using power rules. So we get m sub x is going to be 1/2 integral from 0 to 1 x to the power of 2/3 dx, which is 1/2 times, so we have to add 1 to the exponent, which we get 5/3, so we get 3/5 x to the power of 5/3 from 0 to 1. I'm just going to make sure if I differentiate, I would get 5/3 x to the power of 2/3, which would cancel with that, so that is good. So we get 3/10 as the answer for m sub x. M sub y is integral from 0 to 1 x times cube root of x dx. This is the integral from 0 to 1 x to the power of 4/3 dx. Add 1 to the exponent, so we get 7/3, so that would be 3/7 x to the power of 4/3, or rather 7/3, 0 to 1, and this would give us 3/7. And then the last thing we need to evaluate is the area, and area is integral from 0 to 1 of the difference of the two functions. The top one is cube root of x, this is y equals cube root of x, and the bottom one is just 0. And this is x to the power of 4/3 times 3/4 from 0 to 1. So this would give us 3/4. Now, x bar is going to be m sub y divided by area, which is m sub y is given as 3/7, and area is given as 3/4. So this would be 4/7. Y bar is m sub x over area. M sub x is 3/10. Area is 3/4, and that would give us 2/5. So the center of gravity is always going to have to be written as one single point. So the x component, so let me write it down. The center of gravity is, x component is 4/7 and y component is 2/5. So that is the answer. Let's look at one more example. Find the center of gravity of a quarter disk of radius r. So again, we'll draw a diagram. Always draw a diagram first. We will evaluate the center of mass. center of gravity using the same formulas again. So for that, we need to find the two functions, function on top and function at the bottom. So this is a quarter disk of radius r. So the equation is x squared plus y squared equals r squared. We can solve for y because we need the function. We get y equals the square root of r squared minus x squared. Notice that I placed the origin at the center of the disk to make things simpler. So this is y. So the top one is y equals root r squared minus x squared. So I can say m sub x is equal to 1/2 integral from 0 to r. So again, m sub x was the one with the difference of squares. So it's f of x squared, so it's root r squared minus x squared minus 0 squared dx. So that's m sub x. This would be 1/2 integral from 0 to r squared minus x squared dx. And this gives us, we can easily integrate this. We get 1/2 r squared x minus x cubed over 3 from 0 to r. Plug in r, we get 1/2 r cubed minus r cubed over 3. Plug in 0, we get 0. So this would be, this is 2/3 r cubed, so that's r cubed over 3. Now we have to find m sub y. M sub y is integral from 0 to r again, x times f of x, which is root r squared minus x squared, minus g of x, which is 0 dx. Now this one requires a u substitution, so we do u equals r squared minus x squared. We get du equals negative 2x dx, and then we can plug it in, we get integral. So x dx is negative 1/2 du. This is x dx, which I can replace by negative 1/2 du. And the rest of it is root u, because u is r squared minus x squared. Now, notice that I have to change the limits of integration because I'm going from dx to du. So changing the limits of integration, if x is 0, u is r squared. And if x is r, u is 0. So we get negative 1/2, and then u to the power of 1/2 becomes u to the power of 3/2, and then times 2/3 from r squared to 0. If you plug in 0, you get 0. If you plug in r squared, you get, so this is going to be plus 1/3 times r cubed. So we get r cubed over 3. And then we'll have to find the area. So for the area, you could do the integral from 0 to r of root r squared minus x squared dx. This is difficult to evaluate. We will learn how to evaluate these types of integrals later. But we don't really need this for this particular problem because we already know the area is the area of a circle. So we have a formula for the area of a circle. So we can just go ahead and find the area using 1/4 of pi r squared. So this is the formula for the area of a circle divided by 4. So that tells us that x bar, which is m sub y divided by area, is going to be, so we have 1/4 pi r squared at the bottom. And then we have m sub y. M sub y is r cubed over 3. And simplifying, we get r on top. We're left with r on top. We're left with pi at the bottom, 3 at the bottom, and 4 on top. And y bar becomes m sub x divided by area. So this would be, again, m sub x was the same thing. If you look at the computation that we did, we got r cubed over 3. So it's r cubed over 3 divided by 1/4 pi r squared. And that is 4r over 3 pi. So the center of mass, or the center of gravity, is 4r over 3 pi, comma, 4r over 3 pi. Now notice that this is something that we could have used a shortcut to obtain, because if you look at the quarter circle is symmetric about the line y equals x. Because it's symmetric, so in other words, if I take a point inside the region here, the reflection about the line y equals x is going to be inside the same region. So it's symmetric about that line. Because of that, center of gravity would have to be on that line. So we could have used that shortcut to evaluate only one of them. So note that y equals x is an axis of symmetry. So y bar and x bar would be the same. That way you could avoid, so you don't have to do this, but this would be a shortcut. You could avoid doing both of the computations. You could do just one of the computations. Okay, next example. Find the center of gravity of the region bounded by the parabola x squared plus 3, y equals x squared plus 3, and the line y equals x plus 5. Let me first find the intersection of these two, and then I'll graph them. So y equals x squared plus 3, y equals x plus 5. We have x squared plus 3 equals x plus 5. So we get x squared minus x minus 2 equals 0. So that gives us x plus 1 times x minus 2 equals 0. So the two solutions are -1 and 2. Those are the two solutions. So at -1, if I plug in -1, I would get x equals 4. And at 2, I would get x equals 7. So maybe we need a little bit more space here. Doesn't have to be a perfect graph, but you do need to graph to make sure that you are clear on what's going on here. So we have -1's 4. This is one of the points on the line. And then we have 2, 7. So this, let's say this is 7, so this is 2, 7. So the line goes through these 2 points. The other one is a parabola, so it looks like this. And the vertex is at 0, 3. So it looks like this. So it is 3 here. So that is our region. So the region looks like this. Okay, so next we'll have to find the moment. So we have m sub x. M sub x is, again, 1/2 integral. Limits of integration are -1 to 2. F of x squared. So we have the top one at x squared, which is x plus 5 squared, minus the bottom one squared, which is x squared plus 3 squared dx. This would be moment with respect to x. I'm going to leave the computation to you to get it done, but you have to expand and simplify. M sub y is going to be the integral from -1 to 2, x times f of x minus g of x. So f of x is x plus 5 minus x squared minus 3 dx. For that, you'll have to first distribute. So you get x squared. We have 2, so plus 2x minus x cubed dx. After you evaluate these, then we also need the area. So area is the integral from -1 to 2 of f of x minus g of x dx. So I'll leave these to you to evaluate. And then we'll have to use these two. So let me just indicate that these need to be evaluated. But again, these are all polynomials, so they are all relatively easy to evaluate. And then x bar becomes m sub y over a, and y bar becomes m sub x over a. And these must be calculated. Okay, so one more example. Find the center of gravity of the region in the first quadrant bounded by these two curves. So we have y equals x cubed and y equals cube root of x. these are the two curves. This is y equals cube root of x. This is y equals x cubed. Now, because these two are inverse functions, they are reflections about the line y equals x. So because of that, we can actually say that the center of gravity would have to be on this line. This is the line y equals x. So that's a shortcut that you can use. Let's find the intersection. So x cubed equals cube root of x. Tells us that x to the 9th minus x equals 0. I cube both sides and move the x to the other side. We get x times x to the 8th minus 1 equals 0. So that gives us x equals 0 or plus or minus 1. We are only interested in the portion in the first quadrant. So this is the region R that we're using. So we don't need to worry about R, x equals -1. And then we will have to find the area and the moment. Area is the integral from 0 to 1 of x cube root of x, which is the top one, minus x cubed dx. This is, again, this is pretty easy to evaluate because these are, again, powered by power rule. We can evaluate these. And then we need to find the moment. So moment with respect to x is going to be the integral, 1/2 the integral from 0 to 1 of cube root of x squared minus x cubed squared dx. You evaluate these, again, pretty straightforward. And then you can get y bar as m sub x over area. Now note that because of symmetry, x bar and y bar are the same. And you can verify that by doing m sub y, but you don't have to do that. If you want to do m sub y, it would be the integral from 0 to 1 of x times cube root of x minus x cubed. So to summarize, this is what we learned in this video, that we can find the moment of the region between f of x and g of x, between y equals f of x and y equals g of x, and x between a and b by these formulas. So moment with respect to x is 1/2 integral from a to b of f of x squared minus g of x squared. Moment with respect to the y-axis is integral from a to b of x times f of x minus g of x, and x bar is always m sub y divided by area. Y bar is always m sub x divided by area. And from calculus 1, we know that area is the integral of the difference of the two functions. And that brings me to the end of this video. I will see you in the next video.